Okay, let's unpack this. Today, we are doing a deep dive into the global market for something that, well, I might sound a bit niche at first. Ion exchange compounds.
Yeah, they do sound technical, don't they? But you should think of them as these really crucial materials. They're used everywhere, purifying water, separating chemicals in like industrial settings,
Right.
and even in pharmaceuticals or food production. They're basically the workhorses for filtering things out, separating stuff.
Exactly. Workhorses, I like that. And to, get a handle on where this central market is actually heading, we've been digging into a pretty detailed forecast report. This one's from Cognitive Market Research,
Hmm.
and it's packed with projections, goes all the way out to 2033, covers regions, countries, the whole globe, really.
And our mission for you today is to sort of cut through all that specific data. We want to pull out the important bits, the nuggets, right? Understand the big picture trends, see where the big growth is happening, and figure out what these numbers are, really telling us about where this industry is going globally.
Okay, and let's give you that high-level global snapshot right up front.
Yeah,
Because the numbers, well, they tell a pretty clear story. Expansion.
definitely.
This market, back in 2021, it generated over $2 billion in revenue. Uh, Specifically, around $2.1 billion, actually,
Okay.
and the projection. By 2033, it's set to nearly double. We're talking almost $4 billion, just shy of $4 billion.
Wow. That points to a really steady global growth rate, doesn't it? Averaging just under, what, 5.5% per year over that whole period?
Yeah, the CAGR is 5.48%.
Right. And for a market this size, hitting a consistent CAGR like 5.48%, that really signals robust, widespread demand. It's not just a blip.
Right. Solid, steady growth, global scale. So the next question is obvious.
Right.
Where's that growth actually coming from? Let's break it down region by region, see what the
Mhm.
report says.
Yeah, and this is where it gets interesting because you see how the market size and the growth rates really vary. It gives us clues about, regional dynamics, industrial activity, that sort of thing.
Absolutely. Okay, starting with North America.
Yeah.
It represented a pretty significant chunk of the market, right?
Mm-hmm.
Pulled in over $560 million back in 2021
Mm-hmm. A big piece.
and is projected to grow steadily, expected to cross the $1 billion mark by 2033.
So that's a strong growth path. Even for a mature market like North America, the CAGR there is just over 5% for the region.
Right.
A little below the global average maybe, but in actual dollar terms, that's a huge increase.
Definitely. And within North America, no surprise, the United States is clearly the heavyweight.
Yeah.
It accounted for well over $400 million in 2021 forecast, over $760 million by 2033.
And the US AGR looks very close to that regional average. So it suggests, consistent demand, probably from its big established industrial base.
Makes sense?
The report does mention Canada and Mexico too, also showing growth. But yeah, the US is definitely the main engine for North America.
Okay, let's hop across the Atlantic. Europe. This region is also a major piece of the global pie,
Hmm.
recorded over $440 million in 2021, and it's projected to grow to around $800 million by 2033.
Okay, so Europe's projected CAGR just over 5.2%. That's pretty much bang on the global average, isn't it?
It is.
So that indicates similar underlying drivers to North America, most likely. Same kind of demand pressures.
And the report gives us details for several European countries.
Right.
Germany, for instance, key market.
Uh,
Over $75 million in 2021,
right.
forecast to nearly double, around $146 million by 2033.
Wow, nearly double.
The UK is also notable, showing strong growth, too, from around $47 million up to nearly $90 million.
And you see significant numbers really across the board in Europe, don't you? France, Russia, Italy, Spain, others listed too. They all show projected growth hitting, tens of millions or more. It really underscores that the demand isn't just in one or two spots in Europe, it's spread out.
Okay, now, here's where it gets really interesting, I think. Asia Pacific.
Ah, yes.
This region doesn't just show strong performance, it shows the highest projected growth rate among the major regions.
That's right. Asia Pacific was already the largest market globally back in 2021, around $770 million. So significantly ahead of North America and Europe even then.
And projected to reach, get this, $1.5 billion by 2033.
$1.5 billion. Huge.
And that CAGR confirms the energy there, over 6.1% for the region.
Wow.
That growth rate is, noticeably faster than North America or Europe.
And China is just a massive driver here, isn't it? Started at nearly $290 million in 2021.
Yeah.
Projected to more than double, over $600 million by 2033.
Incredible. India also really stands out. Robust growth there, too, going from over $130 million to nearly $290 million.
Another one projected to more than double.
Exactly.
Yeah.
Japan, still a substantial market, projected over $170 million. And Southeast Asia, sort of collectively, expected over $220 million by 2033.
So if you connect this to the bigger picture, this really strong growth in Asia Pacific, especially driven by China and India, it strongly suggests, well, rapid industrial expansion, maybe,
Yeah.
and potentially increasing environmental regulations in those economies, creating huge demand for these compounds.
That makes a lot of sense. Okay, let's look at South America next. This region contributed over $130 million in 2021, projected for solid growth too, reaching nearly $300 million by 2033.
And Brazil looks like the standout market in South America, projected to hit over $100 million by 2033.
Roughly doubling from 2021.
Yeah, another double. The report also points out growth in Argentina, Colombia, Peru, Chile, all reaching pretty significant market values too.
Okay. Then the Middle East also shows a clear upward trend, posted close to $100 million in 2021,
Mm-hmm.
expected to grow to over $160 million by 2033.
And Saudi Arabia is listed as the largest market there, projected around $60 million by 33, followed by Turkey and the UAE. It indicates, localized industrial and infrastructure development driving that demand.
Right, specific projects maybe. Finally, we have Africa, contributed over $80 million in 2021 and projected to hit over $150 million by 2033.
And within Africa, the report notes South Africa is the largest market, projected over $64 million by 2033. Nigeria also showing significant numbers.
So it shows that the growth really isn't just confined to those, let's say, traditional industrial powerhouses, right? It's expanding pretty much globally.
Exactly.
So, okay, what does all this tell us when we pull it together?
Well, it really confirms that the global market for these ion exchange compounds is seeing significant and really widespread growth. That seems clear.
Yeah.
And while those established markets, North America, Europe, they keep growing steadily, right, contributing big dollar volumes,
Sure.
the fastest expansion is clearly projected for Asia Pacific, fueled by that rapid development in places like China and India.
Right.
The numbers from the report, they really paint a picture of a market with consistent fundamental demand. And that demand is projected to keep increasing across most regions over the next decade or so.
Yeah, the detailed numbers, even when we kind of round them for discussion, they truly highlight how widespread this expansion is. It's not just a couple of hotspots. It's a global phenomenon, but with certain areas definitely accelerating faster.
Exactly right. It shows that whatever needs these compounds are addressing water purification, chemical separation, whatever it is, those needs are present and growing pretty much everywhere on a global scale.
Okay, so let's wrap up this deep dive. We'll leave you with a thought to consider. Given this steady, widespread growth we're seeing in the numbers right across different regions and countries, what are the fundamental industrial or maybe environmental needs globally that are consistently driving this demand for ion exchange compounds? Right. And maybe how might those underlying needs evolve further by 2033? Welcome to the deep dive. So imagine this tiny chemical workhorse. Probably never given it a second thought, but it's like absolutely essential for cleaning the water you drink, making sure medicines are pure, even refining sugar. We're talking about ion exchange compounds.
Yeah, and for this deep dive, we're looking at a really comprehensive overview from cognitive market research. It sort of lays out the whole market scene, what's driving growth, the roadblocks, and, the key trends shaping things.
Right. Our mission today is basically to sift through this source material and pull out the key takeaways for you. The core market dynamics, what's fueling demand, what's holding it back, and what are the innovations coming down the pipeline.
It might sound a bit niche chemistry-wise, but honestly, it touches so many critical parts of, modern life and industry.
Exactly. Okay, so let's jump in. Looking at the source, it points to some really, really powerful drivers for this market. And the first one, well, it feels incredibly relevant right now.
What?
Water.
Oh, absolutely. The increasing global pressure on clean water scarcity, safety concerns, all of that is a huge factor. Ion exchange is just fundamental in municipal industrial water treatment.
Okay, water treatment. But what are these compounds specifically doing? Is it just like a fancy filter?
Not quite. Think of it more like a targeted chemical swap. These resins, that's the compounds we're talking about, they have these charged sites on their surface,
First sight. Okay.
and they basically grab unwanted dissolved ions, dissolved salts, heavy metals, nitrates, that kind of stuff, and they swap them out for harmless ions that are already on the resin.
Ah, okay. So it's a chemical thing, not just physical filtering.
Exactly. And it's especially vital in, say, water-stressed areas or places with pollution issues, both for drinking water and treating wastewater before it goes back into the environment.
That makes a lot more sense.
Yeah.
So beyond just general water treatment, where else is the demand coming from, according to the source?
Well, the industrial and power sectors are massive users. Think about places needing ultra-pure water. Power plants, chemical manufacturing, oil refining.
Why that pure, though? Can't they just use, like, regular tap water after treatment?
Not really. Even small amounts of impurities, like minerals, can cause huge problems. Scale buildup in boilers, for instance, or corrosion in cooling towers. It can even mess up sensitive chemical reactions.
Right, leading to breakdowns and stuff.
Exactly. Expensive downtime, potential damage. So, ion exchange is essential for demineralizing and deionizing water to meet these incredibly strict standards. And as industry grows, especially in emerging economies, that need for ultra pure water just, well, it skyrockets.
Okay, so industrial expansion equals more demand for this super specific water purity. Got it. Now, the source also mentioned something I found really interesting. Pharmaceuticals and biotech.
Oh, yeah, they rely heavily on ion exchange. But it's not just for the water they use in manufacturing, although that's part of it. It's fundamental to purifying the actual drugs.
Wait, purifying the drug, so it's like part of making the medicine itself. How's that work?
Precisely. It's used in processes like chromatography,
Right.
which is basically a sophisticated way to separate different molecules out of a mixture.
Okay.
Ion exchange chromatography uses these charged resins specifically to isolate the active drug compound from impurities or, unwanted byproducts from the manufacturing process. It's absolutely critical for getting that incredibly high purity needed for pharmaceuticals, especially things like injectables.
Mm.
And with the global boom in biopharmaceuticals, this purification step is just, well, non-negotiable.
That's a level of precision I hadn't really considered. It's not just cleaning the water for the process, it's baked into making the product safe and effective.
Okay.
What's the final big driver the source highlights?
Food and beverage, you see ion exchange resins used in things like sugar refining, dairy processing, making soft drinks and juices.
Is that again about the water purity for making, say, soda? Or is it doing something else?
It can be about the water, but also more specialized jobs, like decolorization, taking out unwanted colors from sugar, for example, or demineralization, which can affect the taste, the texture, even the shelf life of products.
Oh.
So as consumers demand safer, more consistent, higher quality food and drinks, manufacturers are turning to these resins to fine-tune those characteristics.
Okay, so we've got these really strong demand drivers. The basic need for clean water, heavy industry's purity obsession, the absolute necessity in pharma, and quality control in food and bev. But the source doesn't just paint a rosy picture, does it? What are the hurdles, the restraints?
That's right. It's definitely not all straightforward. The first major hurdle the source points out is, well, cost.
Cost, is that the initial investment or ongoing expenses? Or both?
It's really both, unfortunately. The capital cost to install these systems can be pretty steep. That's a barrier right there, especially for smaller outfits or in, less developed regions. But the running costs add up too. The resins themselves, particularly the high purity or specialty ones, aren't cheap. And remember, we talked about regeneration.
Yeah, cleaning the resins to reuse them.
Right. The chemicals needed for that process add a significant chunk to the operational budget.
Okay, so cost is a big one, upfront and ongoing. What else is holding things back?
Well, the flip side of trapping all those contaminants is, what do you do with the resins once they're full or worn out? Disposal and environmental concerns are a major restraint.
Because they're now loaded with potentially nasty stuff.
Exactly. Depending on what they've been used to remove heavy metals, certain chemicals, the spent resins themselves, might actually be classified as hazardous waste,
Oh, right.
which makes getting rid of them complicated, highly regulated, and, again, costly. And navigating those increasingly strict environmental rules just adds more burden and expense.
Yeah, I can see that being a real headache. Does the source mention? Are there other ways to get similar results, maybe without these disposal issues?
And this raises an important question. Yes, there are definitely competing technologies out there. The source specifically mentions things like reverse osmosis, nanofiltration, membrane bioreactors.
Okay, alternatives. Are they gaining traction? Do they offer, like, different advantages?
The source suggests they are definitely strong competitors. Sometimes these alternatives can offer similar or even better performance in certain specific applications. And a key difference often is that some, like reverse osmosis, rely more on physical separation through a membrane rather than chemical exchange.
Ah, so maybe fewer chemicals involved overall.
Potentially, yeah. Fewer chemical inputs for regeneration, possibly different kinds of waste streams to deal with. That can make them more attractive in certain situations or depending on local regulations.
So it's not just about raw performance, but the whole life cycle chemicals. Waste.
Yeah.
Makes sense. What's the final restraint mentioned?
It comes down to the resins themselves and their lifespan specifically, something called fouling.
Fouling. What exactly is that?
Basically, over time, stuff like organic matter, iron, maybe microbial growth biofilms can build up on the surface of the resin beads. It kind of coats them or clogs up the pores.
Okay, gums up the works.
Pretty much. This fouling reduces the resin's ability to grab those ions, so it becomes less efficient. It means you need to do regular, sometimes quite intensive cleaning cycles, or eventually you just have to replace the resin entirely.
And both cleaning and replacing add costs and reduce efficiency.
Exactly. Adds to the operational costs and means the system isn't working at peak performance all the time.
Right. So high costs, tricky disposal, competition, and the resins degrading.
Mm.
Those are some significant challenges. But the source also talks about innovation, right? What trends are shaping the future here?
Yeah, absolutely. The source highlights several key trends, and they seem aimed squarely at tackling some of those restraints we just talked about. One major one is advancements in specialty and selective resins.
Okay, so instead of general-purpose resins, one's designed to target very specific things.
Precisely. Developing resins that are, like, super selective for particular tricky contaminants, think arsenic, boron, nitrates, maybe those PFAS chemicals everyone's talking about.
And how does that help with the challenges?
Well, it's about efficiency. If a resin is really good at grabbing just the one thing you want to remove, you might need less resin overall. You might use fewer chemicals for regeneration because you're not stripping off a bunch of other stuff. And the resin might even last longer because it's not getting clogged up with things you don't care about.
Ah, so it hits cost, lifespan, maybe even the waste issue.
Exactly. It aligns with efficiency goals and often environmental ones, too.
That makes sense. A targeted approach.
Mm.
What about tackling the disposal and environmental side more directly?
Yeah, what's fascinating here is the industry's push towards sustainability, specifically looking at eco-friendly and bio-based resins.
Bio-based, like made from plants or something.
Yeah. Sort of, yeah. Or at least using renewable raw materials instead of just petroleum feedstocks. There's research into biodegradable resins, too. The main goal is to reduce the environmental footprint of the resin itself and, crucially, make that end-of-life disposal, which we saw as a big pain point, simpler and less damaging.
That sounds like a potentially huge shift if they can crack it. Okay, and the third major trend.
That would be integrating smart monitoring and automation, bringing digital tech into ion exchange systems.
Ah, the ubiquitous digital transformation. How does that apply here?
Think IoT sensors embedded in the system, real-time water quality monitoring, clever analytics, automated controls.
Okay, so what does that let you do?
It allows operators to know precisely how saturated a resin bed is, like right now. So you can optimize regeneration cycles, only regenerate when it's actually needed, not just on a fixed schedule. Saves chemicals, saves water, saves energy.
And probably helps predict problems.
Yes. Predict maintenance needs, monitor performance remotely, flag issues quickly. It all minimizes downtime, cuts down on chemical use, and just generally boosts operational efficiency, which again ties back to tackling that cost restraint.
Right, making the whole operation smarter and tighter. So lots of innovation aimed at the weak spots. The source also gives a quick peek at the companies involved, doesn't it?
It does, yeah. It notes the market's a mix. You've got your big global players alongside smaller regional companies. And it mentions many are investing heavily in digital tools to handle challenges like complex regulations, supply chain hiccups, volatile raw material prices.
And it names a few examples.
Yeah, just to give a flavor, it mentions names like Dow DuPont, Purolite, LanXMIS, Mitsubishi Chemical, Resin Tech. Gives you an idea of the key players shaping the market.
Okay. And is this market the same everywhere, or does it vary geographically?
Oh, definitely varies. If we connect this to the bigger picture, production and consumption patterns are really different region by region.
Why is that?
It comes down to local factors. Things like, is there easy access to the raw materials needed to make the resins? What's the existing industrial base like? How much water treatment infrastructure is there? What are the local environmental
Right.
rules?
Different needs, different rules.
Exactly. Demand in, say, a water scarce region with lots of heavy industry is going to look completely different from demand in a place with abundant clean water and
Yeah.
maybe more food processing.
Okay, so there we have it. A pretty deep dive into the world of ion exchange compounds, drawing on that cognitive market research overview. We've seen how these kind of hidden compounds are just vital, driven by really fundamental needs: clean water, industrial purity, pharma safety, food quality.
Yeah, and we've also walked through the real challenges they face. The high costs, the tricky business of waste disposal, tough competition from alternatives like membranes, and just the fact that resins wear out or get fouled.
But crucially, we also saw how innovation is stepping up, directly tackling those challenges with smarter, more selective resins, the move towards greener materials, and bringing digital intelligence into managing the systems.
It's definitely not some static old technology. It's clearly evolving to meet today's needs and overcome its own limitations.
Absolutely. Which kind of leaves us with this final thought, really pulling from the source material. Given those persistent challenges, cost, disposal, competition from alternatives, how might these advancements we're seeing, the specialty resins targeting specific nasties, the eco-friendly push, the smart systems, how might that fundamentally shift which applications choose ion exchange over other options in the years ahead?
Yeah. Will these innovations let it capture new niches, or is it more about defending its current turf against those alternatives?
This is something to think about.